In this lecture, we will further discuss about the meaning of negative temperature and how negative temperature can affect the various quantities that we have discussed so far, that is partition function, internal energy and entropy. We have already discussed that under what conditions this temperature can be negative. And if you recall the previous lecture, we considered two-level system, and in this lecture also our discussion is also going to be on two-level system. In two-level system, we discussed that if the population of upper level exceeds that of the lower level, then the temperature will be negative. Now let us see how it affects the partition function. Partition function Q will be equal to G0 plus G1 exponential minus E upon KT for a two-level system, right? If there is a degeneracy, or if the system is non-degenerate, let us say for non-degenerate systems, non-degenerate energy levels, then Q can be written as 1 plus exponential minus E upon KT. Our now goal is to discuss T varying from plus 0 to infinity and T varying from minus 0 to infinity. Remember that the formula does not restrict temperature less than 0. First, let us talk about T greater than 0. We talk in general about extremes, but the variation over entire temperature range is shown in this figure. Let us first talk about T approaching a value of plus 0. If T is plus 0, then Q will be equal to 1 plus exponential minus infinity. That means Q will approach a value of 1, and that is what you see over here. Now let us take the other extreme. When T approaches plus infinity, then Q will be equal to 1 plus exponential minus E over K into infinity is infinity. This becomes, that means Q approaches a value of 2. Either it will approach a value of 2 or it will be approaching a value of G0 plus G1. So that is why here the variation is not ended at 2, but it can depend upon degeneracies. If both are non-degenerate, then it will be approaching a value of 2. So we have explained this variation, and this is T is equal to 0 and positive onwards. This discussion we have had in other numerical problems earlier. Now let us talk about T approaching a value of minus 0 from negative side. Then Q is equal to 1 plus exponential minus 0, minus becomes positive. I am talking about here, substituting here, minus 0, minus becomes positive, and what I have is minus E upon KT is 0. This is exponential. Since minus becomes positive, this will be. So that means Q becomes very high. In fact, moving towards infinity. And that is what you see over here. It's rising very sharply when temperature is approaching -0, then Q is increasing very sharply. Let us now discuss the next one when T approaches -infinity. Then Q will be approaching what? 1 plus exponential plus e upon infinity, which is 1 plus exponential 0. That means Q will approach a value of 2, and that is what you see over here. So for a two-level system, see how the partition functions varies with temperature when you consider positive side of the temperature or negative side of the temperature. But the point that is to be noted over here, that there is a discontinuity. It is not continuous. At T is equal to 0, there is a discontinuity. Let us talk about the internal energy also. For a two-level system, the partition function is like this. An internal energy is also showing a discontinuity. The way we have shown it for partition function, same way we can show for the internal energy. Let's do that. Since we are talking about two-level system, and let me take the simplest one, 0 and E. So what I have is Q is equal to 1 plus exponential minus beta E. This is Q for this system. U minus U0 will be equal to minus N by Q del Q by del beta at constant volume, that we know. So what I have now is U minus U0 is equal to minus N divided by 1 plus exponential minus beta E into derivative of this exponential minus beta E into minus E. So I have U minus U0 is equal to N times E into exponential minus beta E. Negative negatives are consumed to become positive sign, 1 plus exponential minus beta E. I can rewrite this U minus U0. If I multiply and divide by exponential beta E, then I get this over exponential beta E plus 1. This is how the internal energy will vary with the temperature. We will discuss it little bit more. So we have derived now this expression, that internal energy is given by NE divided by exponential beta E plus 1. Let us discuss the conditions. When beta approaches a value of infinity, when beta approaches infinity, beta is equal to 1 over kT. Okay, remember beta is 1 over kT. When beta approaches infinity means temperature approaches 0. Temperature approaches 0. So then U will approach a value of 0. Because when beta approaches infinity, temperature approaches 0, U approaches 0. And when do we have the total energy equal to 0? When all the molecules are in the ground state. That means this situation, U approaches 0 as beta approaches infinity, that is as T approaches 0 when only the lower state is occupied. And you can notice over here also, when T approaches 0, then internal energy approaches a value of 0. Okay, now let us consider the next extreme when beta approaches a value of 0, let's say, when beta approaches a value of 0, that means t is approaching a value of infinity. In that case, what will be u minus u0? U minus u0 will be ne divided by exponential beta is 0 tending to 0, 0 plus 1, which is 0.5 times ne. And that is what you are seeing over here. When temperature becomes very, very high, the value of u by ne is approaching 0.5. Let us now consider the other case. When beta approaches minus infinity, that means t will approach a value of minus 0. Then what happens? Then u will be what? U minus u0 will be equal to t is minus 0. That means you have ne divided by, when beta is minus infinity, that means 1 over infinity, which becomes 0, right? I can write here beta is exponential minus infinity plus 1. This is equal to n times e. That means u divided by ne will approach a value of 1. That's what you see here. The next one, when beta approaches minus 0, that means t approaches minus infinity, then what we have? Then u minus u0 is equal to ne over exponential 0, in fact minus 0 plus 1, exponential 0 or exponential minus 0 is 1, which is 0.5 ne. That is what you see over here. So the variation is from 1 to 0.5, and here is from 0 to 0.5. It's another way of looking at that when the temperature becomes very high, then both the states are equally likely to be populated. So therefore, the value will start from 0 to half. U by ne will become half. Let us read the comments. Note that u approaches 0 and beta approaches infinity, that is as t approaches 0 when only the lower state is occupied, and u approaches ne as beta approaches minus infinity, that is t approaches minus 0. We see that a state with t is equal to minus 0, here you see, is hotter than the one t is equal to plus 0. So you see the meaning of t negative minus 0 is hotter than the one with t plus 0. And also note down that in this figure, as you see, what we see is that q and u show sharp discontinuities. We see sharp discontinuities on passing through 0, and t is equal to plus 0 corresponding to all populations in the lower state is distinct from t is equal to minus 0 where all the population is in the upper state. This is consistent with when we introduced that when the temperature can be negative for a two-level system. This is how the internal energy will change with temperature on both sides of t equal to 0. Let's further discuss now what does it mean. When t is equal to 0 or t greater than 0 or t less than 0, we notice there is a sharp discontinuity. we also notice that when T is positive, that means we are talking about when you're approaching T is equal to plus 0, you're talking about cooling, cold. But when we are talking about T negative and when T is approaching minus 0, you can see here the system here is much hotter than the one which is equal to T plus 0. Are these discontinuities carried to when we talk about entropy? We'll see about entropy here. And we can use the same expression that we derived for U minus U0. What we have, S is equal to U minus U0. We had N E over, I'll retain T here, and you have exponential beta E plus 1. This is U minus U0 by T plus Nk log Q is 1 plus exponential minus beta E. This is for a two-level system. We are talking about two-level system. Here we see some continuity. Let's say when I talk about T approaching 0, then beta is approaching infinity. Beta is 1 over kT. And then what is the value of S approaching? If beta is infinity, then since infinity is appearing in denominator, this term, first term, this disappears. And if I put beta as infinity, exponential minus infinity is 0, and nk log 1 in that case is 0. I repeat, when beta approaching infinity, there is infinity in the denominator, so this disappears, and beta is infinity, exponential minus infinity is 0, so I have nk log 1 is 0, that means in this case S approaches 0. And you can notice over here. And when T approaches infinity, then beta approaches 0, then what do we have? When beta approaches 0, T approaches infinity, then we have T here in the denominator, so this term disappears. And beta approaches 0, then this term becomes 1, exponential minus beta E becomes 1. That means in that case, your S will approach a value of nk log 2. And log 2 is 0.693. And that is what you observe the value here, over here. It approaches a value of 0.693. Similarly, you can talk about when T approaches minus infinity. Minus infinity. Anyway, when infinity comes in the denominator, the first term will become 0. And T is minus infinity, that means beta is approaching minus 0. So therefore, when you put beta is minus 0, exponential 0, and here what you have, S will approach nk log 2, and that's what you observe over here. Therefore, the entropy of the system is 0 on either side of T equal to 0 and rises to nk log 2 as T approaches plus minus infinity. At T plus 0, only one state is accessible, and that is the lower state. Now note down that the functions that we just plotted, for example, if I start from partition function, the partition function here was plotted against kT by epsilon, and in the next one, internal energy was plotted against kT by epsilon, and even entropy, when we talked about, was plotted against kT by epsilon. And if instead of kT by epsilon I choose to plot against epsilon upon kT, then the variation is going to be as shown in these figures. Okay, so the behavior of the plot obviously will depend upon how we represent it. Now we can get a little bit more insights into the dependence of thermodynamic properties on temperature that can be obtained by noting the thermodynamic result. The thermodynamic result that I am talking about here is T is equal to del U by del S at constant volume. From where this comes? First law of thermodynamics, du is equal to dq plus dw. And you remember that the fundamental equation, what was that? dq is equal to tds, that means I will write du is equal to tds minus pdv, dw is minus pdv. So therefore, I can connect del u, del s with temperature. I can have a pure thermodynamic definition of temperature. That means the pure thermodynamic definition of temperature thus becomes T is equal to del U by del S at constant volume. It comes from this. You fix the volume constant and T becomes del U by del S at constant volume. If you plot entropy in the units of S by Nk against internal energy, it will show this kind of behavior, and that you can obtain by using the appropriate expressions. But what is more important here is to recognize that when S is plotted against U for a two-level system, we see that entropy rises as the energy is supplied to the system, provided T is greater than 0. However, the entropy decreases as the energy is supplied at T less than 0. So what does it mean? That if you supply energy, del U is positive, and the entropy decreases, del S is negative, that means we are talking about negative temperature. Physically, the increase in entropy for T greater than 0 corresponds to increasing accessibility of the upper state, we have discussed it earlier, and the decrease for T less than 0 corresponds to shift towards population of the upper state alone as more energy is packed into the system. Same thing we have discussed in the earlier slides. Recall the second law of thermodynamics. The efficiency of heat engines, which of course is a direct consequence of second law, is given by 1 minus T cold by T hot. Fine. That means if the temperature of the cold reservoir is negative, if T is negative, then this negative becomes plus. Then the efficiency of engine may be greater than 1 if we talk about the negative temperature. This condition corresponds to amplification of signals achieved in lasers. As I said, that this advanced level you will study later on. Alternatively, what is the meaning of efficiency greater than 1? It means that heat can be converted completely into work provided the heat is withdrawn from a reservoir which is at a negative temperature. Now, if both the reservoirs are at negative temperatures, then efficiency is less than 1, as in the thermal equilibrium. Because if both are negative, negative become positive, and overall negative sign remains over there. Now, this all discussion may lead us to conclusion which is accepted and as mentioned in several textbooks, that the third law may require a slight amendment on account of discontinuity of populations across T equal to 0. Based upon our discussion that how these various thermodynamic quantities vary when T is on the positive side of 0 or on the negative side of 0. And what the amendment is suggested is that it is impossible in a finite number of steps to cool any system down to +0 or to heat any system above -0. So what we have discussed in this lecture is that when negative temperature is possible, what is the meaning of negative temperature, and how the negative temperature can affect the variation of thermodynamic properties as a function of temperature. How to achieve this negative temperature, or under what conditions, what techniques can be used to describe this negative temperature, are beyond the scope of current discussion. You will study at a later level, but I am sure that the meaning of negative temperature is clearer. Thank you very much.